Semiconductors have had a monumental impact on our society. Semiconductors are used to make microprocessor chips, as well as being used in the production of diodes and transistors. Semiconductors are at the heart of all electronic devices. Modern aircraft use electronic components in many of their systems, including automatic flight controls, navigation and engine control systems. In this lesson, we will look at what a semiconductor is, and at the makeup and operation of diodes and transistors. We will begin the lesson by reviewing the atomic construction of conductors and insulators. The simplest atom is the hydrogen atom. It consists of a nucleus containing one proton, positively charged, with one electron, negatively charged, orbiting about the nucleus. Conductors and insulators have more complex atoms, with greater but equal numbers of protons and electrons, with the latter orbiting the nucleus in multiple orbits or shells. The nuclei of all atoms, except hydrogen, also contain neutrons. They play no part in the electronic process, so we can ignore them. The electrons in the outer shell of an atom are known as the valence electrons. Electrons in the outer shells may be less tightly bonded to their parent atom than those on the inner shells, and are free to move from one atom to the next. These valence electrons, known as free electrons, form the basis for electrical current flow within the material. Conductors possess large numbers of free electrons. This allows current to flow easily through the material. Gold, silver and copper are all examples of good conductors. Insulators possess few free electrons. This means that it is difficult to get current to flow through them. Mica and glass are examples of good insulators. Semiconductors, as their name would imply, fall somewhere between conductors and insulators. Silicon and germanium are the two semiconductor elements that are used in the production of electronic components. By far the most commonly used is silicon, which is a very common naturally occurring element. It is, for instance, the main element in sand. Silicon and germanium, along with carbon, have a unique property in their electron structure. Each has 4 valence electrons in its outer orbit. As shown in this simplified diagram, the 4 electrons form perfect bonds, known as covalent bonds, with 4 neighbouring atoms creating a lattice. All of the outer electrons in a pure silicon or germanium crystal are involved in perfect covalent bonds, so they can't move around. A pure silicon or germanium crystal is somewhere between a conductor and an insulator. Very little electricity will flow through it. You can change the behavior of silicon or germanium and make it into a conductor by a process known as doping. In doping, a very small amount of an impurity is mixed into the silicon or germanium crystal. Doping produces 2 new materials, known as N-type and P-type material. In N-type doping, antimony or arsenic is added to the semiconductor material in small quantities. Antimony and arsenic each have 5 outer electrons. So when they get into the silicon or germanium lattice, the 5th electron has nothing to bond to, so it's free to move around. As you can see in this simplified diagram, when an EMF is applied, the free electrons move through the material from atom to atom, creating a current flow. N-type material is a good conductor. Electrons have a negative charge, hence the name N-type. However, it should be noted that the material itself remains electrically neutral. There are always an equal number of protons and electrons within the material. In p-type doping, aluminium or indium, each of which has only 3 outer electrons, is the dopant. When mixed into the semiconductor material lattice, they form holes in the lattice where an electron has nothing to bond to. Holes can appear to conduct current. A hole happily accepts an electron from a neighbour, moving the hole to the neighbouring electron. As you can see in this simple animation, when an EMF is applied, the hole appears to move through the material from right to left, causing an electron flow in the opposite direction. The absence of an electron creates the illusion of a positive charge, hence the name p-type. P-type semiconductor material is a good conductor. Again, it should be noted that it possesses no electrical charge, there being an equal number of electrons and protons in the material at all times. A junction diode, which consists of a piece of N-type material fused to a piece of p-type material, is the simplest possible semiconductor device. In this diagram, we're using white circles to indicate holes, and green dashes the free electrons in the two materials. At the junction of the two materials, some free electrons from the N-type material migrate across the boundary to fill holes in the p-type, and similarly, holes migrate the other way. This migration produces positive ions in the N material and negative ions in the p material. This in turn produces a charged region at the junction, known as the depletion layer, and creates an electrical potential, known as the barrier potential, across the junction. The positive and negative ions in the depletion layer repel holes and electrons, preventing further electron or hole movement between the materials. The barrier potential may be represented as an imaginary battery, although it should be remembered that the regions of increased positive and negative charge exist only across the junction. The material as a whole possesses no electrical charge. If we now connect an external EMF across the material, with the positive terminal connected to the N-type material and the negative terminal to the P, electrons will be attracted to the positive terminal and will be pulled from the N side of the junction. Similarly, holes will be attracted away from the P side of the junction towards the negative terminal. This increases the number of positive and negative ions, deepening the depletion layer. Apart from a very small leakage current, this deepening of the depletion layer prevents current flow across the junction. The junction is said to be reversed biased. If the polarity of the external EMF is reversed, so that the positive terminal is connected to the p-type material and the negative terminal to the N, the holes in the p-type material will now be pushed to the right, towards the junction, and the free electrons in the N-type to the left, again towards the junction. In the junction region, the free electrons and holes combine. Thus the barrier potential is overcome, and current will flow freely through the junction. In this configuration, the junction is said to be forward biased. The junction diode then acts as a rectifier, allowing current to flow through it in one direction only. As a reminder, Here is the electrical symbol for a diode rectifier. We will now look at the bipolar or junction transistor. There are two types of junction transistor. They are known as the NPN transistor and the PNP transistor. The NPN transistor consists of a thin layer of P-type material sandwiched between two pieces of N-type material, whilst the PNP transistor has a thin layer of N-type material sandwiched between two pieces of P-type material. The three regions of either type of transistor are known as the collector, the base, and the emitter. The circuit symbol for each transistor is shown here. As you can see, the symbols differ only in regard to the direction of the arrow between the base and the emitter. The arrow always points in the direction of conventional current flow. For an NPN transistor, it points from base to emitter, and for a PNP, from emitter to base. The theory governing the flow of current in a transistor is complex and beyond the scope of this course, so we will limit ourselves to a very basic explanation of the operation. We will have a look at the operation of the two types of transistor, beginning with the NPN type. If we apply an EMF across the collector-emitter region of an NPN transistor, as shown here, remembering back to the junction diode, one of the junctions will be forward biased, but the other will be reverse biased, so no current will flow in the circuit. However, if we apply a small EMF, known as a bias voltage, across the base emitter region, changes take place in the material which will allow current to flow freely from the collector to the emitter. The ability of a transistor to control a large collector-emitter current by means of a small base emitter current means it can act as a switch or electrical relay by turning the small base emitter EMF on and off, thus controlling the current flow in the collector-emitter circuit. The transistor can also act as an amplifier. If a small AC voltage signal is superimposed on the bias voltage, it will produce directly proportional variations in the collector-emitter current. A PNP transistor's operation and function is similar in all respects to that of an NPN transistor, except that the polarities of the applied EMFs are reversed. So now the conventional current flows from the emitter to the base, and from the emitter to the collector. In conjunction with the junction diode and other electronic components, such as resistors, capacitors, and inductors, the applications for the transistor are almost limitless. Furthermore, the ability to control precisely those areas to which doping is applied means that all of these components can be incorporated into a highly sophisticated and complex circuit within a single small piece of silicon or silicon chip. That is the end of the lesson. Here are the main points. Semiconductors, as their name would imply, fall somewhere between conductors and insulators. Germanium and silicon are the two semiconductor elements that are used in the production of electronic components. You can change the behavior of silicon or germanium and turn it into a conductor by a process known as doping. In N-type doping, antimony or arsenic is added to the semiconductor material in small quantities, producing free electrons. In p-type doping, aluminium or indium is the dopant. This produces holes in the lattice structure. A junction diode consists of a piece of n-type material fused to a piece of p-type material. A junction diode allows current to flow freely through it in one direction, but resists current flow in the opposite direction. A transistor can act as either an electrical switch or as an amplifier.